Good morning, everyone. Ladies and gentlemen, welcome to this HITB live stream. This virtual lab is going to be on the topic you can see on your screen. I just want to cross check whether I'm audible and you guys can see my screen. So if you guys can just ping on the chat with a thumbs up or a yes. Okay, all right. Thank you very much for confirming. So I would just like to request all of you to please mute your microphone and turn off your videos if you haven't yet, so that you don't unintentionally interrupt between the live stream and other participants are not disturbed. You may ask your questions if you guys are already on the Discord channel created for this particular workshop. So you can ping there your questions and you can all mutually discuss your questions there. Also, you can ping your questions on this chat. Other teammates from my team are unfortunately not here to support me for this question and answer discussion in the chats. So it will only be me who will answer the questions. So I will just keep looking into the questions and maybe I will just clear out those doubts at the end of the presentation or at the end of the module which we cover. So we will be covering this workshop in 4 different parts. I hope that we will be completing this workshop in the time. So I'll just start. All right. So as you can see on your screen that this workshop is all about signal processing with GNURadio and SDRs. Some of you are already familiar with these terms, signal processing, GNURadio, and software-defined radios, which is basically abbreviated as SDRs. So I'm presenting this workshop in this live stream. My name is Ateet Kumar, and I'm a senior security researcher in Zenith Lab, which is basically a company owned by a Digital 14 LLC. It is based in Abu Dhabi. So I'll just start with the content. All right. So here is a brief about me. As I mentioned that I work as a senior security researcher in Zenith Lab in Abu Dhabi. So I am known here as the signals guy. I have a graduation degree in electronics and communication engineering. So basically I'm an electronics and communication engineer. That's why you can guess that my interest into the radio frequencies, the software defined radio stuff, electromagnetics, antennas, microwaves, all these topics are my domain. Apart from that, I worked as a research fellow in DRDO for 3 years. So DRDO is basically Defense Research and Development Organization in India. It's a very premier organization, specifically established for defense research and development. And it's the only type of, one of its kind of organization in India. If you want to compare it, you can compare it with Department of Defense US. So as I mentioned earlier that we will be covering this workshop in basically 4 parts. Part 1 will be the basics of EM and radio frequency. Part 2 will be the digital signal processing techniques. Part 3 will be GNURadio hands-on, and Part 4 will be software-defined radios, RF hacking hands-on. So last 2 parts are all practicals. So I just hope that you guys have received the emails for installation of GNURadio on time and you are already ready with the GNURadio on your Linux or Windows system. I also hope that most of you guys who are joining here with the interest of RF hacking and software-defined radio stuff might be having some kind of software-defined radio with you, whether it be RTL, SDR, or HackRF. In case you don't have any, then it's not a problem. This workshop, I think, is getting recorded, and you can always look back and see how this thing is done with the software-defined radios hardware kit. You can buy easily from market. I will tell you which one to buy in the later part of this presentation. So let's begin with the electromagnetic spectrum. So those of you who are already from the science background, you might have studied this term in your high schools, in physics. So if I speak in general about the electromagnetic stuff, it's basically everything, every frequency you see in this universe, on this planet, in the sky, in the space. It's all is a part of electromagnetic spectrum. Even the visible light is a part of electromagnetic spectrum. But as you can see, this colored strip portion in this diagram represents the visible light of the electromagnetic spectrum. Apart from that, there is a lot more to this electromagnetic spectrum. There are many kinds of electromagnetic waves. Some of them we already know, like radio waves, AM radio waves, microwaves. We use microwave at home, so it's related to that. FM radio waves, TV waves. You already know about X-rays. You guys might have seen this stuff in the hospitals. And gamma rays, basically related to the outer space. Also in some phenomena on this planet Earth also. So this huge electromagnetic spectrum, it starts from okay. So there are basically two terms in which you can define a frequency in the electromagnetic spectrum. So either you can define it in terms of the wavelength, which is basically measured in terms of distance, like meters, centimeters, nanometers, millimeters. Otherwise, you can just convert it to the frequency. So sometimes it is very easier to define electromagnetic wave in the units of frequency. Sometimes it is easier to define it in the units of wavelength. So there is a huge range of frequencies, or we can say wavelengths, which we cover into the electromagnetic spectrum. Obviously, at a point of time, not all of them are our area of interest. So sometimes we just restrict ourselves into the radio waves. Sometimes we just restrict ourselves into the microwave domain. And yeah, so you can always refer to a table or a diagram like this if you want to know what frequency range covers under what part of the electromagnetic spectrum. So either you can use wavelength or you can use frequency as a reference. Now here in this table, you can see on one side, frequency and wavelength both are mentioned to describe what is referred to on the right side. So there are basically defined frequency bands. So we have categorized the electromagnetic spectrum for our simplicity into the different bands so that we can study each band, and it is easier to operate in these bands. So if I talk about some 30 to 300 hertz of the frequencies, these are extremely low frequencies. And as you can see in the column of wavelength, it converts to the order of 10 raised to power 4 to 10 raised to power 3 kilometers. So what exactly is meant by this thing? Basically, wavelength is defining in some way the length of the antenna you might be using, because frequency is directly convertible to wavelength. and electromagnetic waves are defined by either wavelength and frequency. So if you want to build an antenna, let's say for extremely low frequency, it would be at a length of 10 raised to power 3 kilometers or so. It depends on what type of antenna you are creating, but the order of the antenna dimension will be similar to this distance. So it is highly impossible to build an antenna of this length. Of course, there are some techniques through which we can still build or design such kind of antenna with such huge dimensions on this earth, but this is very complicated because you don't want to get into this problem in your day-to-day applications. So that's why we go to the higher band of frequencies, which we call mostly high or very high frequencies. So we operate into the high frequency ranges so that the antenna dimensions are reduced significantly. For an example, I can tell you that if you have ever looked into your mobile phones, opening the cases of mobile phones and looking at the size of the antenna there, it's basically in the dimensions of millimeters, right? Sometimes the outer fabrication of the antenna looks like a millimeter dimension, but the antenna is very small in the nanometers dimension. So if we go higher on the frequency range, we will find that the frequency range up to 300 gigahertz is considered to be part of microwaves. So up till this frequency, we use these electromagnetic spectrum in our day-to-day applications, like mobile communications, satellite communication, TV, FM radios, sometimes ham radios, walkie-talkies. So if I just generalize the radio waves, I can say that it belongs to the band of starting from 30 hertz to 300 gigahertz, which also includes the microwave frequencies. Sometimes in some articles, in some books, you will find radio waves are categorized differently from the microwaves because microwaves lie into the order of 100 gigahertz. So sometimes you will find that microwave section is different from radio waves, starting from some 1 gigahertz and ending up to 300 gigahertz. But in many of the books or on many of the articles, you'll find people refer to microwaves as a radio waves only. So as I mentioned that you can define the radio waves in terms of frequency or wavelengths. In nature or in general, the radio waves or electromagnetic waves are generated by accelerating electric charges. So if you have accelerated electric charges, let's say in an electric current, there is a flow of electric charge, and if the electric charge is being accelerated through an external force or naturally, it will generate a radio wave. Similarly, if the electric charge is oscillating, it will generate an electromagnetic wave. So that's what exactly happens in the antennas. When we feed the antenna with power, the electron, the current, the electric charges flows through the antenna body, and they just move to the airspace from the antenna body. Basically, they just change the medium while oscillating. So this oscillation of these charges between the antenna dipole creates the electromagnetic pulses there, the electromagnetic waves there. So outer space, apart from this planet Earth, outer space also generates a lot of radio waves because there are a lot of cosmic activities happening, some stars bursting, some new explosions happening. So you might have also heard in the news that scientists have discovered some weird frequency signals, radio frequency signals, which is supposed to be some million light years ago generated into the space. So it is basically the radio frequencies or any electromagnetic wave, they travel with the speed of light. That is why in order to do a specific kind of measurements in outer space or to know more about this universe, we can say, that we use this specific property of electromagnetic waves, so the radio waves, to know about the phenomena, to study about the space. So if there is any cosmic phenomena happening inside the outer space, you might probably receive a radio frequency associated with that. Sometimes it's a gamma radio band. Sometimes it's what you say, X-ray radio bands. So you can observe the outer space in terms of frequencies. That's why we have these radio observatories at different places of the world to observe about the outer space. Let me just briefly, is there a mic on? I can feel some interruption. Whoever is having a mic on, can you please just turn it off? You guys make sure that your mic and video is turned off. All right. So radio frequency communication system, it can be categorized in 3 different types of communication systems. Any kind of communication system basically have these 3 different types. So the first one is very simple. It is called simplex. It is only one-way communication where you can only transmit from one point and you can receive at the other end, but you cannot do it the other way. Then the second one is half duplex system or half duplex radio communication system, where at any single point of time only one device can act as the transmitter and the other device can act as a receiver. Then at the other point of time, the second device can transmit and the other device can receive, but they cannot do it simultaneously. So they cannot be at a single point of time, they cannot behave as a transmitter and a receiver. Then the most important one is the duplex systems, because we use it in our daily life. If I give an example of the mobile communication, you talk on the phone to someone and you can call and you can speak, you can also listen to the other person at the same time. You don't have to stop talking while you want to listen to the other person. So if I have to give an example of half duplex radio, it is basically, you might have seen these walkie-talkies in most of the places. Police people and the security personnel, they use this walkie-talkie for their communication. So it tunes into one channel, they just press a button and only one person can speak at a time, and then he has to stop transmitting and then he receives the audio from the other side. Now let me just briefly go through the wireless communication system. So basically, in any kind of communication system, we convert a low frequency message signal to a high frequency signal by using modulation techniques. So we use a carrier signal, which is marked here in this diagram as a C of T. So basically it's a time domain signal denoted by C. The message signal denoted by M here is a very low frequency signal. So by low frequency signal, I mean, just let's assume that I am speaking. So my audio signal is a low frequency signal and I want to transmit this audio signal to a very long distance. I want to use a high frequency signal so that my audio signal can be modulated over the carrier, and this resulted signal can be transmitted over longer distances. Also, one of the important factors why we use modulation techniques in any kind of communication is to reduce the size of antenna. As I already mentioned, that if you have a low frequency for transmission, your antenna size is significantly larger, and it is highly impractical and impossible to build large antenna sizes for small purpose of communication. So we always use high frequencies for the modulation, and we convert the basic low frequency signal to a resulted high frequency signal, and then we transmit using a antenna which can be reduced to a nanometer or a millimeter size, or maybe to some meter size is also practical. So that's why we use modulation in general. So we convert the low frequency signal into the modulated waveform using a modulator. And then we also need to amplify, because while doing all this process, there is a significant loss into the quality of the signal due to the system noise, due to the channel noise. So if you are using an electronic device, the electronic device will induce some kind of electronic noise into the signal, which will hamper the quality of this original message. So you always need to amplify. Also, you need to amplify to boost the power of the signal, so that you can easily transmit it with sufficient power that on the other end, if the receiver receives it, it should be able to recover the signal in complete sense in order to recreate the original message. On the other end, on the receiver side, there is an antenna which is a similar type of antenna we have used in the transmitter side. I just want to point out a term in antenna domain. It is called the polarization of the antenna. You guys can note about polarization. You guys can read about polarization. It's how to say? Basically, when we talk about antennas, there are different types of polarization of antennas we use. So if our polarization mismatch between the transmitter and the receiver, you will not be able to receive the signal you want to receive at the receiver end, because it all works with the electromagnetic how the electromagnetic wave propagates into the airspace or in any medium. So when the electromagnetic waves are traversing through a medium, there is a significant change in the properties of electromagnetic waves. So that's why we consider that if we have to use the same kind of polarization on both ends of the transmitter and receiver in order to receive the electromagnetic wave. Otherwise, we will not be able to see the signal we want to receive on the receiver end, and we might probably end up receiving some noise, and we say it as a failed communication. So on the receiver end, we use an amplifier again to boost up and to cover up for the loss into the whatever has happened into the channel, because any channel is full of noise. If it is an open wireless channel, it is full of noise from the environment itself. If it is a wire channel, then it might induce some electrical and electronic noises. So that's why we use shielding on the cables when we talk about the wired communication, in order to protect it from outside environmental noise. Then we demodulate. So demodulator is just reverse process of modulation mathematically, and we just use the similar type of components in modulator and demodulator, but in the reverse order. So then we need to amplify the power of the demodulated signal, because after demodulation it will become a low frequency signal again, and we also want to boost up the power of the output to match it to the output device. Let's say we have an output device as a speaker, so we want to boost up the power up to the level that this speaker should operate. So we should be able to hear the audio we want to hear out of the speaker. So there are different types of modulation. The first one, very common, is the amplitude modulation. So it is a very simple type of modulation if we compare to the frequency and phase modulation. So the amplitude modulation, the amplitude of the carrier varies in accordance to the information signal. So information signal is basically the low frequency signal we are talking about, which we want to transmit. Then we come to the frequency modulation. So it is the same thing, but with the frequency. So we have a high frequency carrier signal whose frequency is being modulated in accordance to the information signal or the message signal. Similar thing happens to the phase modulation. The only thing is the parameter we are changing here is the phase. So here there are three equations mentioned, which you will find most probably if you go to read any article or in any textbook about this signal processing, or in general in communication. You will find these three things. The first thing is the carrier signal, which we denote as C of t. So it has the amplitude denoted by capital A. You can denote the, represent the carrier signal or any waveform in the form of sine wave or a cosine wave. Then you have omega c. So omega c is basically, omega is defining the frequency here, and you also add a phase factor here in the equation of the waveform or the signal. So sometimes, for simplicity, we just consider the phase factor to be 0 when we are calculating some mathematics related to the signal. Otherwise, we have to consider this phase factor always, because it changes a lot of property in the signals when we work on the signal and we process the signal into some modulation and demodulation, and we want to transmit it or receive it. So there is a significant change in the frequency, phase, or amplitude, and that's how we define these types of modulation. The message signal is denoted by small m of t. So capital M here denotes the amplitude of the message signal, and the other part denotes the sine wave related to the message signal. So we end up having a modulated output signal, which is in a simple way is basically the carrier signal multiplied with the message signal, but here there is this amplitude which is in addition to this message signal. So we'll look into this how it looks like in actual waveform when we will do the actual signal processing on the GNURadio module. So here this thing has been again explained, the modulation and demodulation thing with this waveform. So you can see there is a low frequency signal which we call the analog baseband signal. So basically in this diagram you can see that digital data, which is basically a string of 1 0, is being converted to analog baseband signal, and then this analog baseband signal is being modulated over the carrier, and the output is being transmitted. So this purple waveform you can see here is the modulated output. On the other end, the receiver end, you receive this modulated output. Of course, the waveform is slightly attenuated. Also, it might be distorted with significant phase delays. So in the receiver part, we take care of all these deviations from the original transmitted signal. So we add a radio carrier here in order to demodulate. So you can see that we are adding a radio carrier in the modulation as well as the demodulation part. And then we are receiving, we are able to demodulate the received signal, and we are getting an analog baseband signal again, which we can convert into the bit stream which we originally transmitted. It is not very simple as it looks like here in this diagram, because there are a lot of processing involved into all this process. So we'll talk about that in a while. So as I mentioned, in the types of modulation, AM, FM, and PM, these are basically related to analog modulation in general. And now if we talk about the digital modulation, similarly, we have amplitude shifting, which we denote as ASK, frequency shifting, and phase shifting. So in amplitude shifting, we can see that as the amplitude is shifting, as the amplitude is changing, we can mark it as a 1 or a 0. So a lower amplitude can be denoted as a 0 in the signal, and the higher amplitude can be denoted as a 1. So we can basically represent this analog signal which has this changes in the amplitude levels into the binary form. So this converts down this signal to a digital form which we can process into our computers. We can do digital signal processing over this stuff. So it is in very general sense. Obviously, there is a lot of processing and mathematics involved behind this. So, but I just want to cover up the very basics of this so that you guys understand that how it looks like in general. Similarly, if we talk about the frequency shifting, you can see the frequency of the signal is changing. So where we have the low frequency part, we can represent it as a 0. Where we have the high frequency part, we can represent it as a 1. That's how we can convert this frequency frequency shifting signal to a digital signal representing zeros and one streams. Now, phase shifting, you can see clearly that there is a significant phase shift here, which is almost reversal here. So if you have, let's say, I assume that my positive phase, I will represent it as 1. So whenever I will have a reverse phase, which is 180-degree reversal phase shift, I will denote it as a 0. So wherever there is a phase shift, I will represent it as either 1 or a 0. That's how I can use the phase difference or phase reversal to represent it into the digital form. Let's begin with the part 2, and after finishing the part 2, we'll have a short break before we go to the practical session. So part 2, we will discuss about the digital signal processing. As you can see on your screen, I'm not sure if you are able to read this smaller text here, but this is a diagram which is explaining the use and applications of digital signal processing. And by the size of this diagram, obviously it doesn't cover everything we use the digital signal processing for, but it gives you an idea that how important digital signal processing is in today's world. So you can find the digital signal processing finds application in space, in commercial applications, in telephone communication, in military, in scientific applications, industrial and medical as well. So it is basically covering almost all walks of the communication part. Also, apart from communication, we use it for processing data, like image processing. When we use facial recognition system, we use image processing. We collect the data, we process the data into the digital format, and then we generate some sort of output, and then we compare this output and we authenticate. So this is a simple example of the use of digital signal processing. Another use of digital signal processing is, if you guys have ever heard or read about these traffic monitoring systems. So let's say I want to differentiate between the vehicles and let's say I want to differentiate between cars and people walking. So I will use a huge amount of digital signal processing there by the camera feed, and then I will differentiate and classify each entity into whether it is a vehicle, it is a bicycle, it is a person walking on the road. So this is what we use in traffic monitoring, or in general, we can use such systems also in places where we want to monitor the security of an area or a perimeter in basically classified areas, let's say in military applications. We also use a lot of digital signal processing in radar applications. So in earlier days when radar was invented, there was not much digital signal processing happening there, because it was basically designed to find out the range of a target. But now with the modern day radars, you can even classify the category of the target. Let's say if I take an example from military, let's say if you want to identify your target, whether it is a F-16 aircraft or it is a F-22 aircraft or it is just a bird flying in the sky. So this outcome you can generate with a huge amount of digital signal processing running in the background. So you take the data from the radar, you process it digitally, and then you classify, categorize your target. So this kind of stuff we use the digital signal processing for. So there is a lot of mathematics involved behind the digital signal processing, but for this workshop, I will just restrict to the very basics, so that those of you who are still beginner in this signal processing domain, they can go back and read about different topics in the digital signal processing, and for their reference, they can also study the mathematics behind that if they have a lot of interest how this thing works into the computers and in general in academics. So here you can see there is a time domain and frequency domain signal plot of the sine wave. So the upper diagram number A shows the sine wave in the time domain. You can see the time is on the horizontal axis, and on the vertical axis we have the amplitude level. If we convert this time domain signal and if we want to see it in the frequency domain, what we see is only a frequency peak here, only a frequency spike here. So this signal is a 6 gigahertz signal. If you look into the time domain, you can easily locate the amplitude level of the signal. But if you don't know the frequency of the signal, you have to calculate it, basically measuring the time period and converting it into the frequency. If I see it in the frequency domain, I can easily see that at point number 6, there is a spike here, and on other points there is only 0. So there is only one signal I can say which belongs to 6 gigahertz and having an amplitude of 5. So why I'm showing this diagram to you, because when we do the signal processing stuff, whether it is we are doing it in softwares or we want to build a hardware, we always have to deal with the time domain analysis and the frequency domain analysis. So to compare between the time domain and frequency domain analysis, because in general the signals in nature, they don't exist like one frequency can be uniquely identified. They don't exist like that. There is always a mixture of lot of frequencies. So if we talk about multiple signals and we want to see the multiple signals in time domain, we won't be able to identify each of the signals uniquely. But if we convert them into the frequency domain, because all those frequency can be discretely identified in the frequency axis, we can easily locate what signal we are looking for, and we can differentiate between different frequencies. So it's pretty much easier to operate in the frequency domain to analyze the signal in the frequency domains rather to use the time domain. All right. So here is the example of what I just explained to you. So we have a combination of different frequencies on the upper diagram. You can see this pink color waveform. Let's say it is a frequency f, and then this blue color waveform is having a frequency 3 times of the f, and this black color waveform is having a frequency 9 times of the f. So you can see in the time domain analysis part, we are clearly not able to see each signal distinctly. Of course, this is only 3 signals, so you should be able to differentiate easily. Also, there is color marking, but in general, if you try to receive a signal into a spectrum analyzer or a software-defined radio hardware, if you do the analysis on the time domain, you won't be able to locate each frequency discretely. So in order to identify each frequency associated with each signal discretely, we need to convert this whole thing into the frequency domain. So in the frequency domain, you can see this pink color spike belongs to the frequency f, this blue color belongs to the frequency 3 times of f, and this higher frequency 9 times of f is denoted by black color. We can discretely identify each of the frequencies. So it is very simpler when we operate in the frequency domain. If I want to just extract out this frequency f, I can easily do it with a very low pass filter, and I can just exclude these frequencies, the higher frequencies from my output. So I don't have to care about, so these high frequencies will work as a noise for me. I will just neglect those frequencies. I'll just cut out those frequencies using a simple filter. There is one important thing you might want to note down. If a signal does not change at all, its frequency is 0. If a signal changes instantaneously, its frequency is infinite. Anything between that is what we call the operation area for signal processing. One more important technique in the digital signal processing, which we often use when we use GNURadio or software-defined stuff, is the Fourier transform. So in general, in the modern day signal processing, we use actually the fast Fourier transforms, which are the faster algorithms of discrete Fourier transform. But the basics of that all comes down to the Fourier transform. So Fourier transform is a mathematical tool where we convert a time domain signal to a frequency domain signal in order to observe each component of that signal discretely. Also, we can do a reverse thing, that converting the frequency domain signal to a time domain signal. So we have Fourier transform and we have inverse Fourier transform. The equation of both of them are mentioned here. And if you want to read more about the Fourier transform mathematics, so you can just follow this website, fouriertransform.com. It's a very good website where you will find all the mathematics behind how we operate in the Fourier transform, how we use it to convert, to switch between the time domain and the frequency domain. Another important concept is sampling. So sampling is very important when we come to the signal processing or digital signal processing. So basically, as you have observed in the previous slides, that there is a sine wave signal, which is continuous sine wave signal. I'll just draw it for you. So here we have a signal. This green part of the signal you can see is actually the continuous time domain signal. Now, this continuous time domain signal, if we want to observe it, we cannot observe it like every sample we cannot take into the count, because whichever system we will use, it will not be able to measure the amplitude, or it will not be able to detect this signal which is continuously flowing in time domain. So at every instance of time, it is having some sort of value. So let's say I talk about if I want to analyze this signal between 0 and 1, so it will never be a case that at each point of time I will observe this signal. I will miss out some part of this signal, right? So in order to reduce this kind of processing, because if I want to consider every instance of the time and every instance of this continuous signal, I won't be able to process all this data using my computer power of my computer, or let's say of my device, because there are infinite instances of time between this 0 and 1. So if we talk about only this period, there are infinite instances of time, and that means there are infinite values of this continuous time domain signal. But we want to reduce this amount of data to a significant amount of data which we can process into our computer or in our device easily, and it should be faster. It should not be like we are taking years to process a simple signal. So in order to facilitate that, we use a basic technique in signal processing, which is called sampling. What we do is we take samples, discrete samples of this signal, and we recreate the signal, the original signal, using these samples. So we don't need every value of this signal at each instant to be considered. We only need the important samples, which we can convert again back to the original signal. All right. Here, this diagram basically shows you how we begin with sampling. So as you have seen in the previous slide, these blue color spikes are actually the impulse signals, the impulses we are having at each time instance for the sampling. So basically, we are using an impulse signal to extract out the samples at the specific time instances. So an impulse signal in time domain looks like this spike having an amplitude level, and it is only defined at the particular time instance. It is not defined continuously on the time. It is defined on a particular time instance. So if I say that this point 0 is having an impulse signal here, so it will never be extending to 0.5 or negative 0.5. It will always be at only one instant, that is 0. Similarly, we can add the impulses at different time domains to create different time instances to create a train of impulse, which we generally use to sample. So in order to sample a continuous signal, we need an impulse train to extract out the samples at a specific time domain. So if a signal is like this, so what we do is we use a impulse train like this, and we will extract out the signals, the samples from this continuous signal, and it will look like something like this. Okay, I'm sorry, I forgot to clear. All right. So after the sampling, the signal will look like this. So these are all discrete values, and we can easily convert down these discrete values. We can represent the discrete values as discrete samples to operate inside a computer. So we can create a matrix to operate in these discrete values, and we can get an output, and we can again convert back to the original signal by just converting these discrete values to continuous time domain. Another important concept you want to take care about while we are doing signal processing on GNURadio and with the SDRs is the decimation process. So decimation is basically reducing the sampling rate. So what happens is we don't want all the samples to be processed in order to do whatever signal processing we want to do, because a signal can be represented with some n number of samples, and it will still be containing all the information which is there in the original signal. So we don't require all the samples of the signal in order to convey the full information. We just need some samples of the signal to convey the full information. So in order to reduce the sample rate, in order to drop down some samples from the signal, we use the decimation process. So we can just use a simple low pass filtering technique to drop out the samples. So we will be dropping out the higher frequencies, and we'll be considering only the lower frequencies. Basically, we are dropping out the high frequency samples. Decimation is also referred to as downsampling. Decimation factor is simply the ratio between the input sampling rate to the output sampling rate, and it can be just denoted by a ratio. So one more thing important which you need to consider here is decimation. The factor is always an integer. It can never be a fraction. It can never be a prime number. So that's why we always use an integer value for the decimation process. So your ratio of the input rate to the output rate will always come out to be integer value, so that you can define it as a decimation factor. If it doesn't come out to be an integer value, we take the nearest higher integer value for safer side as a decimation factor. So a signal can be downsampled only when in some cases when it is oversampled, then a signal can be downsampled without doing any filtering. Otherwise, we have to do some sort of filtering to downsample the signal. Another important thing is interpolation. So interpolation is just the opposite of decimation. Basically, here we want to cover up, we want to make up for all the drop samples we did in the signal processing part. So all the samples we have dropped might be containing some information which we don't want to lose. So what we do is to maintain the sampling rate to the original, or let's say we have an output module attached to our signal processing module, and this output module might be having some input sampling rate range. So we want to match this sampling rate from the signal processing output to this input of this another module. So we add some zero valued samples into the signal to make up for all the dropped out samples we did in the decimation part. So it is also called zero stuffing. What we do is we just add, let's say I have samples here at different instance of time, and let's say this is the output of the previous signal processing module containing the decimation and filtering part. Now I want to make up for the sampling rate so that I can transmit this data to another module which might be having a sampling rate, let's say S. And in order to maintain this balance between the sampling rate, I want to add some samples which are not having any information or any amplitude, but are basically zeros. So I have added the zero valued samples into this this signal in order to maintain the sampling rate at the output. So this is also called zero stuffing, or it is also called downsampling, basically just the opposite of decimation, or sorry, I made a mistake. It is called as upsampling, just the opposite of decimation. So in order to increase the sampling rate of the output of one system so that the another system operate at the higher sampling rate, we need to use the interpolation. Again, this interpolation value, the factor of interpolation is an integer value, just like the decimation. All right, so we are done with the part 1 and part 2, basically the theory part, and whatever we have discussed so far, we'll be doing all that stuff practically now in the next part. Before that, we'll just take a 5 minutes break. You guys can have coffee, and we'll join back again after 5 minutes, and we'll do the practical stuff with GNURadio and the software-defined radio. Also, if you haven't yet installed the GNURadio, and if you haven't yet installed the related software-defined radio modules, you can do it right now in these 5 minutes, and then let's join back again and do the practical stuff. Okay, welcome back to this workshop. Now we are heading to the part where we will learn how to practically design the modules for software-defined radios and for software signal processing. So whatever we have studied so far in this workshop, of course, there is a lot more to dig deep into if you talk about digital signal processing and also signals in general. And you can always refer textbooks and internet and go read about the stuff, the technical terms, the mathematics which we use to do all kind of signal processing in modern day techniques. But in this limited time frame, I could only cover those topics which I felt that they are really important if we want to begin developing our own GNURadio modules or working with the software-defined radios. So those techniques and the terms which I explained to you in the previous part are all related to what we actually do on the software side of the signal processing. So in present time, we actually don't require, for simple stuff, we don't require to build an electronic device or to use digital components which are basically in the form of hardware to do all kind of signal processing. If you guys might have heard about MATLAB, about Scilab or similar type of softwares, we use those softwares to develop the signal processing modules on the computer, and it's called software signal processing. We can just program our module of signal processing, and we can do all kind of stuff which we earlier used to do by using some electronic hardware or big size equipment containing analog and digital components inside them. So if I want to give you an example, an oscilloscope or a simple spectrum analyzer you might have seen in your laboratories in your college or in your schools, or maybe if you are working in some place where you are involved in some sort of measurement or signal processing, you might have seen an oscilloscope sitting on your table. That kind of huge equipment is having a lot of digital components inside it, a combination of computers for processing and a combination of electronic ICs and modules to perform the required digital signal processing. So if I talk about what is GNURadio, okay, I'm not sure whether all of you have installed GNURadio already, but I'll just show you how to install it in a simple way if you are using a Linux. Right, what's happening? So you can see the Linux terminal. So first you need to do is you need to sudo apt update and press enter. It will update your repositories. Then next command you need to run is sudo apt install GNURadio. You will also see GNURadio dev, but you can just go ahead with GNURadio because it will install the basic GNURadio on your Ubuntu. If you are doing it on Kali, I would recommend that do it or build the GNURadio with the source repository, because if you just use the terminal to install it, sometimes it gives problems, some dependency issues, and you might be stuck in solving those dependency issues for a longer time. So I would suggest if you're using a Kali Linux, just go to the GNURadio tutorial or GNURadio website and just follow the instruction how to install it on Kali Linux from source repository. You can build it, and it won't be showing any dependency issues. Of course, you need to download and install all the dependencies before you start building the GNURadio. So this command will be able to install the basic GNURadio project on your Linux computer, and you should be able to see all the important blocks which we want to use. If you want to add any other GNURadio processing blocks, so you have to find a GitHub repository or some source code for that, and you have to install it out of the tree. It's not all included in this GNURadio project here. So if you download if you build from the source, if you download from the terminal, install from the terminal, you need to add the out of tree modules separately. So you can always go ahead and search on the internet which is the best file, which is the best repository to install the out of the tree modules, and you can build the out of the tree modules into your GNURadio setup. Also, at this point, I would like all of you to install a utility which we require to explain only one topic here. So it is called htop. It's a simple utility to show you the performance of your computer, the parameters of performance. If you already have some application on your computer installed on which you can monitor your CPU consumption and your RAM and memory consumption, you can use that later. I will explain later why I require these to download. Okay, so if you open the GNURadio companion, you will see the first screen like this. On your right side, you will see all the signal processing modules, or the blocks we say. So there are so many things already built into the GNURadio project, and you can use them directly. You don't have to go and look into what's been programmed there, because these are all tested and these are already built and included in the GNURadio project. Here you will find from simple audio sync and sources to all kind of processing modules. So here I would like to mention that GNURadio is an open source project and anyone can contribute to this project. So even you, if you want to build a separate signal processing module and you want to contribute to this community, you can add your signal processing module into the GNURadio. So if you go to the website of GNURadio, you will find some useful information you need to know about GNURadio. This is the official website, gnuradio.org. So here you can see all the releases, and you can go to the documentation of GNURadio to study about the changes from the previous version to the recent version. And you can also go to the Getting Started tab to follow the tutorial for instructions of installation for Windows and Linux. Also, if you go to the About section of GNURadio, you will find the very basics of GNURadio and the software radio here. So it is just an open source software where you can create your signal processing module to support your radio hardware. So you can use this software to build applications which can find use in normal signal processing if you want to do it for your own research, or if you're a hobbyist, or it can also help in building up some applications which you can actually use in some professional kind of signal processing work. So I use and develop these applications for professional work in my company also. So this is a very useful tool, and it's very easier to learn if you know the basics of what signal processing module you're using. So I would suggest that whenever you are selecting a signal processing module in the GNURadio, you first, if you don't know, if you're not familiar about the processing of the block, you first go and read about that topic, because at the back end there is a mathematical equation, or there are multiple mathematical equations which are working. And yes, one important thing to mention here is the backend of all these blocks are in Python. So GNURadio is written in Python. So you can also write your Python program and directly convert them to the GNURadio blocks. Or you can build a GNURadio module here, and it will end up as a Python program in a file which you can use later. So it has both of the things, the programming part and the GUI part. So whichever you are comfortable with, you can use that. Okay. So when we start the GNURadio, we always see this first screen. On the right side, we have all the blocks. To navigate into these blocks, you can either use the mouse directly, but it is very easier that if you search using the search bar. So let's say I want to use a low pass filter. I don't want to search it. I will just type low and it will show whatever is related to this keyword. So I have the low pass filter and low pass filter tabs. I can directly drag and drop here in this window. And now I am already started with building a GNURadio module. So the options block and the variable block are the two blocks which by default you will see there. So this options block is basically defining the ID of your project. So when you save this project, this will be the name of the file you will find in the .py format. So if you want to change this, you can change it, and this will be the top block into the Python program. The variable is a very simple block. We use it if we want to add some parameter which can change value while we are doing the processing. So let's say sampling rate is something which always needs to be changed with the specific requirement. So you just need to change the value and it's done. So let's say I change it to 16,000. Yeah, this ID refers to the name of this block, and I can use this ID into other blocks to refer to this variable. So I can use directly this as a variable, just like we do in the programming. So I don't need to type in a value. I will just use a samp_rate variable into the other modules, and whenever I will change the value here in this variable block, it should change the values in all the blocks which are using the samp_rate as a variable there. I'll just click apply, and you can see the values are changed. Now it is 16 kilohertz sample. Earlier it was 32K. Let's just delete this. Now, as I mentioned, that whatever you are building here is eventually getting converted into a Python code. So whenever we are supposed to input a value or input an expression, it should be a valid Python expression. So I want to, let's say, write 16 kilo, and I will use the scientific notation 16e⁻³ it still shows me the 16K value here. So if I see on the GUI, it is showing me 16K. What if I write 16K here? It becomes red. That means there is something wrong with this block. So we cannot use it. What is wrong is this 16K is not a valid Python expression. Also, you can see in this particular window here that it is saying that 16K cannot be evaluated because it is expecting a valid value here or an expression. So I can write 16,000. I can write 16e⁻³. That should work because both of these are a valid expression in programming. 16K is not understandable by a programming language. Whether it should be a combination of integer and string, it should be character, or it should be considered as 16,000. The computer will not know this. So you have to input a proper value, a valid expression in each of the signal processing blocks. Now I want to show you a very simple example for how to begin with the signal processing module. If you are very, very new to the GNURadio, if you are using it for the first time, so it should make you very happy after you finish it. So I will just take a waveform generator, a signal source. I will drag and drop. If you don't want to drag and drop, you can also just click on the required block and just press enter. It should come up here. If you want to select a block, you can just draw a square around it and it will become highlighted blue color and it will show you the block is selected. Also, if you want to disable or enable the block, let's say I don't want to delete this block, but I want to use it later, not now. So what I can do is I can just click on this block. I will press D on the keyboard it will become gray, and that means that this is disabled. So even if it is connected into the signal processing module, it will not do anything. It will not perform any operation. If I want to enable it again, I will just press E. It is enabled again. So I don't need it. I just delete it. Okay, so we have taken a signal source. So basically, it's a signal generator we have taken here. It's an arbitrary signal generator. If you compare it with the hardware arbitrary signal generator we use, so there we have a limitation which is based on the hardware we are using. So there are hardware signal generators you might find in one of the electronics lab attached to some oscilloscope or a spectrum analyzer. So here you can see different parameters we have to define for this particular block, and it is the same case with each and every block we use in the GNURadio. That's why I said that whenever you are not familiar with any kind of processing module here, first you go and read about that processing module so that you know what are the parameters you need to define every time you want to use that particular block. So in the first part, you see this ID parameter here. So you can give a name. You can leave it like this if you are not referring to it in further part of the module, or you can change this name to something which you want to give and maybe you can remember. Next is the output type. So we have 4 output types here. One is the complex, float, integer, and short. Mostly we switch between complex and float in most of the cases, and in some applications we might require to convert the type of something into the integer or a short value. So if you are a computer student, you already understand the float, int, and short. I will just explain this. What is this complex thing here? So basically, when we talk about the signals, so if we talk about the complex signals, we always have 2 parts of the signal. First is the real part, and the second one is the imaginary part. And these both constitute together a complex signal. And why the complex signal is required? Because whenever we want to measure the in phase and quadrature phase of the signal, we always need the real and imaginary part, basically the complex type of signal. We cannot measure these 2 parts if the signal is not complex type. So in general, the complex type signal we use for all kind of calculations and all kind of processing. So I'll not dig deep into this complex signal domain because it's another topic and it requires a lot of mathematical understanding of these equations related to cos and cosine and sine. So if you want to note down a term, just note the complex signals, and you can always refer from the internet and read about this. So we'll just directly come and begin with the building the signal processing module. So I can either use complex, I can either use the float. I will show you the difference in a while. Now the important thing here is the sampling rate. So we have studied earlier about the sampling, and that converts down to a sampling rate value, which we have to define in any kind of signal processing module, because without the sampling rate, there can be no signal processing, because we cannot just analyze the whole signal in continuous domain if we don't extract the samples and convert it down to the discrete domain. We cannot just analyze. It is not practical, because at any given between any given period, there are infinite time instances and there can be infinite values of the signal, and we don't require all the values to process on the signal. We just require some sufficient amount of samples so that we can process the data and we can generate an output, and we can again convert, recreate the original signal. So we have to give a sampling rate value here. So here also you can either give a sampling rate value directly if you don't want to change this value later, and if you feel that you are going to change the value often, so you can use a variable name. So here I have given the same variable name which I was having in this variable block. If you change the name in the variable block, you have to give the same name here if you want to use that value. Now the type of waveform, there are a lot of type of waveform already defined in the in this block. There can be a constant signal, a sine, cosine, square, triangle, and a sawtooth waveform. So for simplicity, we just leave it here with the cosine. You can also change it to sine waveform. I hope you understand the difference between cosine and sine. Then you have to define a frequency. Here also, it's the same case I explained with the variable block. In the frequency, you have to give a frequency you want to generate this signal for, and you can write it in both ways. Either you can directly write the value, or you can use the notation. So in both ways, it will work. But you cannot write K, or if let's say you want to write 10 megahertz, you cannot write M, or you cannot write MHZ. This is all wrong. This is all invalid. So you have to give a proper expression here. Let's say I give 10,000 value. Amplitude, let's leave it 1. Amplitude is basically the what you measure on the amplitude axis of the signal. So it is basically explaining the level of the voltage level of the signal if you talk about an electrical signal. Just to simply understand this. Now this signal source block is still showing this red text here. So it means that we need to connect this block to something, because this signal has an input port, has an output port which is in blue color. Okay, let me also explain this thing, this blue and this color thing. All right, it's not given here. Okay, if I change this to the float value, you will see the color has now changed to the orange. Earlier it was blue. So each of these type of values are defined with a color coding, so that you don't have to open the block properties and look what type of values you have given here. You can just directly refer to this color and you will know that which value you have. So if I change it to, let's say, integer, it saves a lot of time when you are building a very large signal processing module. So let's just change it to complex, and let's get started with the module. So I want to analyze this signal. I want to see what is the waveform of this signal. So I need a block like an oscilloscope. Basically, I need a screen where I can visualize this waveform. I can see what is running on in the time domain and frequency domain. So what I'll do is I will find a GUI block. So here you can see there are two types of GUIs given here, WX and QT. I would like to mention that in the recent GNURadio release, the WX blocks are not there, only the QT blocks. So it works on the QT. In the earlier versions, it was WX and QT both. So you can use either of them. So let's say because my in my options, I can see it's already QT GUI. I don't want to change it. I'll just use QT GUI. So here are a bunch of options which I can use to visualize my signal. I have a frequency sync. Here I can analyze my signal in frequency domain. I have a time sync. So anything which is named as a sync is basically your output part, and anything which is named as a source is your input part. So we add these sync parts when we want to analyze an output. We want to see an output. So let's say I just connect these two. Okay, now one more thing important. As you can see, this blue color here is for complex. So these two blocks, the output blocks, or any block to which you are connecting your signal processing block, they all should be in the same type. Otherwise, it won't be a valid block. Let's say I change this to float. I click apply. Now it has become red. Basically, these are not compatible because I am passing a complex value to a block which is asking for a float value. So I have to change it to complex. So always take care of this compatibility issue. Well, your block will never run if you have not taken care of these issues. So it is simple to identify. You don't have to make some efforts. All right. So now I want to run this module. Let's change the signal sample rate to the original, which was 32K. Now you want to run this module. Okay. So here is the play button, which I can use to execute this flow graph. So what it will do is you can see here in this left side of the screen. So when I will click on this execute button, it will ask me to save the file. I want to save this file. Let's say hello world.grc. Okay, here we go. So this is how you will be able to analyze your signal. And this is very simple signal processing block. It doesn't do anything. It is just generating a signal which is having a frequency of 10 kilohertz. And you can see it in the time domain and the frequency domain. So here in the upper part, you can see the time domain signal. Okay. So if I hover my cursor here in this window and I just scroll up or down, it will decrease or increase the level here in order to properly visualize what is happening here. Also, if I draw a square or a rectangle here in this window, I should be able to zoom in. But the thing which is difficult is to zoom out. So, okay, one more thing here is you can see these two waveforms. It is really difficult to stare at this waveform. It's blue and the red color, and both are like overlapping each other, but they have a difference. So it's very difficult to look at this. So this, okay, sorry, I need to run it again. Yeah. So this blue color waveform is the real part, and this red color waveform is the imaginary part. Here you can see at the right side, you have real and imaginary. So if I click on the imaginary part, it will turn off the imaginary part, and now I can see only the real signal, which we always like to see. So we never like to see two waveforms for one signal. But if you are representing a signal in a complex domain, it will always show you two waveforms. And I should also mention that this real part and imaginary part are having a phase difference between them. That's why they are not completely overlapping. They have a phase difference. I'll just show it to you. All right, you can see that they have a phase difference here, so that you can actually differentiate between them. So this constructs to the real and imaginary part of the complex number, but you don't want to always want to look into such kind of signal like this. Like you don't want to look at two parts simultaneously, so you can turn any of them off or on. It will be easier to start with. In the lower part, you can see the frequency domain. So here, if I hover my cursor over the speak point, it is showing 10 kilohertz. And you can see here in the frequency axis as well, it is showing 10 kilohertz. So it is showing only one spike of frequency here, because we have the signal which belongs to only a single frequency. It's not multiple frequencies running here. Now let's say I have another signal generator, and I will change the frequency to, let's say, 20 kilohertz, and I click on apply. Now I would like to add these two. I will just type add. I'll drag and drop. I'll connect these two. Make sure you have the compatibility maintained here. It's all blue, so it should be good. All right, now I will run this. Let me just minimize this part. Okay. All right, now okay. Okay, I can see here two different frequencies. This graph is flowing. I will just turn it off. And you can see that the original cosine waveform has now been changed. And if you can, I'm not sure if you are able to identify, but if you observe the signal in the time domain, you won't be realizing that there are two frequencies here. Now, come back to the frequency domain. We have two frequencies here. Okay, it's not showing both of them. Why? Because we have to cover up in the band. We have to cover up in the band. It was showing from -15 to the +15. So let me just change it. It's too much. Let's just do 12 kilohertz. All right. And it should come up in the band we were observing. All right, here it comes. So now if I consider this time domain portion, I'm not able to actually visualize there are two frequencies here. You can't just do that by observing with your eyes. But if you come to the frequency domain analysis, you can see that there are clearly two visible spikes. One is at 10 kilohertz and the another one is at 12 kilohertz. So you can see these two spikes here. So that explains why we require frequency domain analysis for signals, because naturally the signals will not be existing with only one frequency associated with it. It is always be a combination of frequencies, and you want to visualize all the frequency signals discretely so that you can differentiate and you can locate which is your intended signal, and you don't have to waste your time on the noise. So you can clearly identify these two peaks here, and this explains why we use this explains the time versus the frequency domain analysis. If I want to add more signals here, I can add, and you can also select copy and paste if you don't want to search again. So if you just want to use the same block again, you can just click or right click, copy paste, or you can just Control-C, Control-V. So I have a third module here, and I'll just type in frequency 15 kilohertz. I'll click on apply. Okay. Now I have no input port to add this signal here. What I'll do is I'll double click on the add module, and I will change the number of inputs to 3. Click on apply. Now I have one port to connect this and execute this. Okay. So you can see this graph has become more messier now, right? But we can easily identify in the frequency domain that there are three frequencies here: 10 kilohertz, 12 kilohertz, and 15 kilohertz. Okay, I will just explain the sampling rate thing here. So we are giving the sampling rate as to 32 kilo, but if we look in the frequency domain, here you can see that there is 15K and negative 15K. If you just hover your mouse cursor to the extreme point, you'll find that it is 16K on the positive end and negative 16K on the negative end. So this is the lower end of the band, and this is the higher end of the band. The positive side is the higher end of the band. If you take a difference of these, it will come out to 32K, which is exactly your sample rate you have given. So this bandwidth here is related to the sampling rate you are giving initially. So if I change the sampling rate to 60K and execute, all right. So now you can see that this has the negative and positive extremes of the frequency axis have changed to positive 8 and negative 8, which constitutes the 16K band. All right. Okay, so this is how you can start with the basic generation of the signal and visualizing your signal into the GUI. Now, I want to explain that why we use Fourier techniques or the FFT technique in order to process in digital signal processing. So I have a module built already here. I will explain, and meanwhile you can just follow up creating the module on your computer right now. So everything is same. This option and variable block remains same. I just used a single signal source. So I will show you the parameters I have defined. I have not changed anything. The only thing I have changed is I have given a variable here, which shows the frequency variable. So here I have not passed a value. I have passed a variable here. And this variable is defined by QT-GUI range. So you will find QT-GUI range under the QT options. So if you type QT-GUI, you should be able to see this QT-GUI range here. So basically, it will generate a slider kind of thing for you. And you should be able to change the frequency values or change the variable values while you are actually executing your module. So you don't need to stop every time and go back and change the values into the module. You can just slide down to your required values and your processing module will be working. So I have defined the ID as FREQ for frequency. You can also define a label here so that you can easily see and identify what it is. And I have given a default value. Then I have to mention a start and a stop values in order to define the range of this variable. And also you can define number of steps. So if you want to change your value in the like you want to have more number of steps, that means you can change the values with little difference between two values. And if you reduce the number of steps, that means that you'll be changing the values with a big difference between this range. So let's say I click on apply. Okay, so you can see I added the label as frequency. It shows up here, and I have this signal source here. Now I am using this frequency sync and time sync again. I will come back to this throttle module. I just want to show you something about Fourier. So let's execute this. So this is what I was talking about, this slider thing here, you can see. So you can just slide up and down to increase or decrease the frequency. This is pretty much convenient and very easy instead of just stopping your module every time and going back to change the values. You can also write the values here. Let's say I write 500 and press enter. So there is this this changes the value to 500, and yeah, again the real part, imaginary part, because we have defined the signal to be complex. And in the frequency domain, I can see the signal frequency is 500 kilohertz. Sorry, it's 0.5 kilohertz. So it is exactly the same which we have mentioned here. All right. So now, yeah, I want to show this throttle block, what it is doing here. So for that, I think I will just, I'll just stop running the program here. Okay, and then what I need to do is I need to disable this for a while, and I will just connect the signal processing block directly, signal source block directly to the, okay, I'll just take it down. All right. Yeah. Okay. So now I have disabled this throttle block to explain the working of this throttle block. So now I want you to open your terminal, and I told you to download the utility htop. All right. So I just want you to see the performance of your computer without and with this throttle module. So we need to type a command here, which is htop -p and 0. Okay. So now this window is running. I'll just drag it aside and I'll execute my block. All right. So now you can see my signal processing block is up and running. And if you see in this first line, you can see the consumption of my processing power here. All right. So it sometimes goes below 50% and sometimes it goes above. I will just change the frequency and let's see what is happening here. So you can see the performance, see it spikes to 72% sometimes. On your computer, it will be different. So if your computer has a less processing power, then it might consume all of the computer's processing power, all of the CPU power, and your computer may hang or your module can stop working. So in the worst case, you will need to turn off your computer and start again. See, even on my computer, it's an Alienware, still it is consuming a lot of power, and we are literally doing nothing. We are just generating a frequency and just visualizing the frequency on the GUI. It's not even a very complex signal processing module where we are doing a lot of digital signal processing stuff. It's just a single signal frequency. All right. So if I add this throttle block, first let me just delete these connections and I will enable this throttle block here. Now let me execute this. Okay. And now we can see the CPU performance. Okay, so let's increase the frequency. Okay, I have increased the frequency to a significant amount, but I can see it's a minimal consumption of my CPU power here. You can check on your computer as well. There should be a significant difference when we were using we were not using the throttle block and now we are using the throttle block. You can see how much, up to what percentage my CPU consumption has reduced, because it's just a simple program, right? It's not doing anything complex here. just one signal at one frequency. So this throttle block plays an important role when you are defining the sample rates, higher sampling rates, and you're working in a complicated signal processing module where there are a lot of changes in the sampling rate. So basically, this throttle block will save your day. So just keep this thing in mind where whenever you are required to pass one signal with some sample rate to another block, which also requires some sample rate to be maintained, you use the throttle block to facilitate this thing, to maintain the sample rate and with the minimal consumption of the CPU power. All right. So we have to move to the next part where we will explain the requirement of the Fourier transform in the digital signal processing domain. So here I have just created similar module which I showed you in this window. So I have just added one more signal source. As you can see, I have just added one more signal source, and I have added two frequency sliders. All right, and I have added these two signals, a throttle block and a sync block. So now let me just execute this. Okay. Okay, now let's say that in both of the, look at the right corner of the window. You can see on my screen both values of the frequency are at 100 right now. Okay, let's just turn off the imaginary part for now. Now you can see that in the time domain, I can see only one waveform, but I have used two signal sources. It's not one waveform, it's two signal sources. So there should be two waveforms, right? But the only thing I can see is single waveform. Now, in any case, if you are looking into the time domain signal, you will never realize that this is not just one frequency, these are two frequencies, right? Oh, sorry, these are two signals. But why it is showing like this? Because both of the signals are having same frequency. There is no difference in the frequencies. Now, let's change frequency number 2 to some value. Okay. Okay. Now, in the time domain waveform, you can see that there has been a change in the waveform, but still you observe only single waveform because we have added these two signals, right? But now let's say I want to differentiate between the frequency of these two signals. So it won't be very easier to do the time domain analysis here. It is much easier to look directly into the frequency domain. I can see clear two spikes of two frequencies. So I can just hover the cursor here and I can just identify which frequency I have, right? Now, the more you increase the frequency, the farther it will go from the zero center. So let's say I increase the frequency number 2 to the extreme point. It goes to 10 kilohertz. Yeah, it goes to 10 kilohertz here. And let's just reduce the frequency 1 to 0. So frequency 1 is 0. So you can see that we are able to differentiate between the low frequency and the higher frequency. It is very important when we are doing actual signal processing because we always want to reject some frequency components. Let's say I want to reject a higher frequency component and I want to just consider and process the low frequency component. So I will just use a simple filter to only operate on this frequency, and it will never pass the higher frequency of this 10 kilohertz, right? If I want to pass the higher frequency, I'll just use a simple high pass filter which works in this range, and it will reject all the lower frequencies below that. Very important part when we do the basic signal processing and we do the filtering in digital signal processing. Okay, now because I mentioned the low pass and high pass thing, let's just build some low pass filter so that you can learn how to use the filtering. Okay, I have a low pass filter module already built here, but for your reference, I will just build it now so that you can follow. I hope you all understood the concept of why we are using Fourier domain and fast Fourier transform here, and why we are using the frequency domain analysis. It is much simpler to analyze signals in the frequency domain, especially when you have complex type of signals. Okay, now let's say I want to add a noise. In the previous flow graph, which I already built, I used two signal source. So I will just I can explain this. I think it is much easier right now. All right, let's make a new signal processing module. So I have a noise source here. I will drag and drop. You can see this noise type is showing as a Gaussian noise. Okay, so you can see this noise type is a Gaussian noise. The Gaussian noise is the noise which we have, which we refer to in general to the environment noise, because it's like it's totally random and it has no specific characteristic. We define it by the name of Gaussian noise. You can read more about this term Gaussian noise, and you can go into the details. What kind of signal is this? So just note down this term if you want to read more about this, about Gaussian noise. I have taken the amplitude as 1, and let's just leave everything like this. Click OK. Then let's use the audio sync. Okay, with the audio sync module, you always need to take care about one thing, which is the sampling rate. So the audio sampling is slightly different from what we do on the arbitrary signals. So to an arbitrary signal, we can use any kind of sample rate which we require, but for the audio signal processing, we need to have a specific sampling rates. So let's say if I am talking about the audio signal in telephone line, I have to use the sample rate of around 8,000 hertz. And if I talk about the sampling rate of the audio on digital media like CD, I will use a 44.1 kilohertz of the sample rate. So you can refer to this thing, the audio sampling later. But I'll just show you that here we have different values of sampling rate already defined. So I cannot just take a random sample value for this audio sync module. I have to take some sample value which are understandable in audio sampling rate. So these are basically it depends on what kind of audio device you are using. So right now we all will be using the audio cards on our laptops or computers, which generally have the sample rate of 4.1 kilohertz or 48 kilohertz in the modern in the recent computers. So when we want to use the digital audio sampling, we use the 48 kilohertz sampling in general. So I'll just use 48 kilohertz, and we don't need to specify the device here. We'll just click OK. Now you see that this input port of the audio sync is orange, and this output port of the noise source block is blue. So we need to maintain the compatibility, and in the audio we don't have any option to change it to other values. So obviously we are changing the noise source from complex to float value, and we click apply. It's done. Now I will use the FFT, QTGUI, frequency, and time sync. Okay, let's say we use the waterfall sync. It's good for visualizing the filter part here. All right, let's connect these. Okay, again, the blue, we need to make it orange. We need to make it float. All right. So what I did right now is I didn't double click and open the properties of these blocks and change the type from complex to float. You can directly just select these blocks and you can try pressing the arrow buttons up and down. So if I press the arrow button up, they become blue, which is complex. If I press the arrow button down, become orange. If I press further down, becomes gray. So this keeps on changing the type, right? So I will use this, and let's just connect all these blocks. All right. I hope you are able to follow up. In case you are not, then you can always go back to the recording. I just hope that this presentation is being recorded. I'm not sure if any of the moderator from HITB is here, but anyways, I can still send all these signal processing module to, because I have the list of participants, so I can send the emails. I will also give you the link to my GitHub repository. You can go back and look into these signal processing modules on GNURadio later on the GitHub. All right, let's execute this. We need to save it. Let's save it as noise filter.grc. Done. Okay. So in your computers or your laptops, you should be able to listen to the noise sound, which we usually listen on the FM radio when we are not tuned to a particular station. So this is how a noise signal looks like. So if you are connected with a software-defined radio, you would find that wherever there is no signal you are receiving, you will receive such kind of noise. So this is the waterfall image, the spectrum of the Gaussian noise, which is basically in general all kind of noise, random noise. Now, to visualize the filtering process, let's say I use a low pass filter. So low pass filter is basically, it should pass only the lower frequencies and reject all the higher frequencies. So we need to define a range of frequency for the low frequency and then a cutoff frequency above which it will not pass anything. So double click, make sure I make this to the float type because I want to maintain the compatibility. Float type. Decimation, we shall leave it 1 because we are not dealing with the changing sampling rates. And let's change the cutoff frequency to 10,000, transition width to 100. Leave everything like that. Apply, OK. And now I need to connect this low pass filter before I do the other part. I do the visualization of the signal. So I have connected this low pass filter here. You can also remove this audio sync if you don't want to listen to the noise every time. It would be simpler and less distracting. All right. Now let's just execute this. Okay. So here you can see this filter, low pass filter, is only accepting the low frequencies, because you can see a fall in the graph here, both on the both sides. So all other frequencies outside this band, this 10 kilohertz band, will be rejected. So it will only pass the lower frequencies. All right. Now, if let's say I change the, okay, let's add a QTGY range value here, and let's give it a name with cutoff. Default value should be, let's say 2000, and okay, let's say it's 5000 and 10,000 steps. All right. Now I'll just change the cutoff to the variable cut underscore off. Now we should be able to change the value while we are running the program. Okay. So now let's say I increase the cutoff value. You can see it is covering more range than previous. Also, if you change the transition width, which is another important factor in any kind of filter, if you change the transition width, let's say I change the transition width to 200, click apply. Okay, it didn't make much difference here. Let's just increase this value further. 2000. Yeah. Now you can see that earlier there was a sharp fall on both ends of the filter, but now it has become more smooth and the slope has reduced. So this portion of the transition width is basically when you don't want to just reject everything strictly outside the band, and you also want to consider some of the side signals, side frequencies which you might be getting, which have some sort of information from your original signal modulated over those frequencies. So you can always define a sharp or a smooth transition width. So in general, when we talk about the frequency modulated signals like the FM radio stations, we use a smooth filter and a wide filter, because we also want to consider those side frequencies which may be containing the signal information. That's why when you listen to the FM radio station, the audio quality is really, really good as compared to a walkie-talkie, because walkie-talkie is working on amplitude modulation, and your frequency modulation waves it gives you much more quality in the signal. Also, we use a different type of technique which we call as super heterodyning in FM radio signals. So super heterodyning gives you two beat frequencies, which is basically the difference of the higher and lower frequency, and that difference you use to convert down your original signal to a particular frequency for tuning. So this is a low pass filter. It's how it looks like. You can also try seeing the difference between low pass and high pass filter. Okay, let's say I use a high pass filter here. So I just need to repeat the process again. And I just need to define all the parameters. Disable the low pass filter. Let's say the cutoff frequency is 100 kilohertz. Transition width, let's say, is 1000. All right, execute. Okay, there is some error. All right, we can see that there is an error in the sampling rate. And okay, give me a second. All right, let's. Okay, think I need to change this. And it should work correctly. All right, transition width is 100 and cutoff is 10,000. All right, let's see. Okay, it's giving the same error again.
Change the cutoff frequency.
Oh, yes, I think it's cutoff frequency, yeah. Yeah, thank you. Okay, so you can see it is totally opposite of the low pass filter. It is high pass filter and it's only passing the high frequencies and rejecting all the low frequencies. You can see this trough here, and this is the transition part where we have taken a very sharp transition width here for this filter. So that's how you can design your own filter for simple filtering process if you want to analyze a signal. So this is how you can just simply define a filter: a high pass, a low pass. There are other type of filter as well, band pass filters. So you can just read which parameters you have to define for these two. For basic three filters, the low pass, high pass, and the band pass, we only need to define the cutoff and the transition width. You can also see what changes when you change the type of window. There are different type of windowing techniques in the digital signal processing. Hamming and Hanning are common. Then comes Kaiser. Rectangular window technique is also very common. So you can build your module and change these window techniques, and then you can find out that what changes, and you can see what is happening when we change these, when we use the different type of windowing technique. Okay. All right. So this sums up with the filtering part. And now another important topic which we want to cover in order to use GNURadio efficiently is the sample rate. So we haven't actually observed the importance of sample rate yet. So let me just open this module which I have made here. So in this module, I have used a WXGUI just to show you one thing about sample rate, how your sample rate matters here, and how you can just define the the sampling values conveniently. So let me just, okay, you guys can follow up building this on your screen. It should take like three minutes or so. Then I'll explain how it looks like and how it works. Okay, some participants are saying that they don't have WXGUI. Probably then you just see what I'll be showing on the screen, because it's not very required that you build this module and then only you can learn. It's just for the learning purpose about sampling rate, just to explain. And one person has asked, is there anything like a negative frequency? Okay, I don't want to give the complete answer to you, because I want you to read about this, because this is a very interesting question you have asked. When you begin with the signals thing, you always get this confusion that whether we actually have a negative frequency, just like we see in the books or you just saw on the GUI. Actually, there is nothing like a negative value of a frequency here. But when we talk about the frequency domain analysis, we always consider a band of frequencies. So there is always this thing. I mean, I showed you earlier in one of the example that whenever you look into the FFT block, the FFT GUI, you will always see that if your sampling rate is 32,000, the frequency band will show you from -16 to +16. So it is if you just subtract the higher frequency, the lower frequency from the higher frequency, it will come out as 32,000, because it will be a band of frequency. Not so you can bring your negative value of frequency to 0 if you don't make 0 as a center of your analysis. So in this part, when we are not bringing the center of the frequency axis to some particular frequency, we are just leaving it at center 0. That's why it is showing you the band from negative to positive. If you bring your center from 0 to some particular frequency, it will show you the frequency band extending from 0 to the higher value of the frequency. So this is interesting question. Thanks for asking, and it should trigger the same question to other participants as well. And I think that this thing you should try, how to bring your frequency axis from 0 to the higher value you have taken. And this you can do in your GNURadio. So I will just leave it to you as a homework. And it is very simple activity. I'm sure you will learn about this stuff when you start doing this on the GNURadio. So a very interesting question. I'll just take a few minutes to see what people have asked. Okay, everybody is asking that if this presentation is recorded or not. Okay, so because I right now cannot communicate to any of the organizers or moderators of HITB, I'm not sure whether this is getting recorded or not, but one person has said that they can see the host is recording. So I suppose that the host is HITB and they are recording this session. So it shouldn't be a problem. All right, no more questions. Okay, so let's get to the sample rate thing. Okay, so those who don't have a WXGUI, you can just look at the screen and see and learn what I'm going to tell you now. So why I have taken WXGUI, because it's some specific thing I want to show it to you. So let's just execute this graph. What? Okay, here. All right, let's just turn off the imaginary part. And the signal source. Okay, if I turn it off, I need to change everything again. All right. Just press the arrow. Done. So use the shortcuts because it will save your time. All right, there is something wrong here. Okay, let's not just waste the time because it's only one simple thing. I want to show it to you. Okay, now if you are using WXGUI, you will see on the right side there is a tab for marker. If you select, you will see link line, dot large, dot medium, dot small, none. So I'll just select dot large because it's not significantly large enough. On my screen, it's still small. Anyways. Okay, so I have represented this signal here as dots. Now you can see earlier when I was not using the dot, it was looking like a continuous time signal. Because I'm generating it into the software, so it shouldn't be a continuous time signal because that's the thing which is something analog. It's not a digital, it's not discrete. So it shouldn't be like that because computer, it's not generating an analog signal at all. So now if I change it to the dot representation, you can see these dots are not just the random dots. These are samples of this signal. So we have defined a sampling rate of 32,000. You should be able to count 32 different points between one time period. All right. To make it simple, I will reduce the sample rate to let's say 8,000. All right, dot large. Now, if you're following, you can see on your screen as well, the number of dots have reduced, and now the dot is countable to 8. So if I count 1, 2, 3, 4, 5, 6, 7, and 8, and then it's again 1 for the next period. So it's 8 sample points I have taken here. Can you also observe the sharpness in the signal? Because we have reduced the sample rate, the signal is no more smooth enough, right? Let's say I reduce the sample rate further and I make it to 2 kilohertz. Let's see what we are getting. Okay. Dot large. Now the signal has totally disappeared. Why it has happened? Because we have not taken sufficient amount of samples to recreate the original signal. So if this number of samples are not sufficient enough, we will be losing a lot of information from signal, and that means we will never be able to recreate the the signal in the original form. So sample rate is a very critical thing when we talk about signal processing. Now here comes a term which you might want to read about, is the Nyquist sampling criteria. So Nyquist sampling criteria says that in order to recreate the signal, you need at least twice the times of frequency. You need samples equal to twice the times of frequency, right? So if you are sampling at a double rate, only then you should be able to recreate the signal in exact form. But we usually sample on higher rates, not just twice, because we know that we will be losing samples in further signal processing part. So we always oversample the signal to be on safer side. So when we oversample the signal, then comes into the play the decimation part, and when we decimate a signal, we need to recover for the lost in the samples. So we add interpolation at the other end. So this is all connected to the sample rate thing. So to be very careful about the sample rate when you are building any signal processing module, because this will hamper your processing. Also, when you are using a software-defined radio to capture a signal, sampling rate matters, because it's not like that you can see every type of signal with just one value of the sample rate. So your signal should be sampled correctly in order for you to observe the correct message inside the signal or to process it correctly. Okay. So I think this idea of sample rate is understood so far. I can also give you a small experiment for sample rate. I think this should be the one. No, it's not for the sample rate. All right. Okay. Do you guys want me to go more deep into the sample rate thing? Because I can show you a graph which you can use to understand the sample rate. Otherwise, I will just leave it to your homework, and I'll just move to further part because we still have time to finish up this session with the GNURadio, and then we'll switch back to the software-defined radio and see some actual signals. So if anyone is listening to me, can reply with yes or no if you want a separate block for sample rate.
We can continue with it.
All right. All right. Okay. Okay, so we are almost done with the GNURadio part, and there is a lot more to this software because it has a lot of signal processing modules which you can individually go and study and use for your application. So I just covered the important things which anyone who is just starting with the GNURadio thing should know about. Because if you don't understand the concept of Fourier, the concept of sample rate, decimation, interpolation, you will face problems while building your GNURadio module for actual applications. Okay. Now, all right. So this is one. Okay, I should cover this up because it will include some other important concepts in just one flow graph. All right, we have time to finish this part before we go to the SDR. So I'll just explain this one. It should be useful for you. Okay. So what I have done here is I am trying to analyze amplitude shift keying. So I have taken two signal sources and I have multiplied them, passed them through a throttle block, and then this output is going to a channel model. So this part I will explain to you what it is actually. So what happens is this transmission channel model is used to define the behavior of the signal during transmission. So here we are actually defining the properties of an arbitrary channel. So in real applications, we just use channel. Let's say if it is a wireless communication, the channel or the medium will be the air, will be the environment, the atmosphere. So atmosphere has some properties. So any channel, it can be defined by some specific properties which we always need to take care when we are going to process a signal for transmission or for reception as well. So here in this part, this channel model part, some specific parameters are mentioned here. I have not changed anything here, but you can change with the reference to the GNURadio documentation. So I have not given any noise voltage or offset or something just to make it simple, but we need to define a channel modeling here. Next part is the frequency accelerating FIR filter. So this is it is basically frequency translating FIR filter. So frequency translation is another important concept in digital signal processing. What we do in the frequency translation is we want to bring a particular frequency to some particular value by decimating it, right? So let's say I have a frequency which is I consider to be a high frequency, and let's say I have a 0 point here, and I have a frequency part at some place on some frequency between, let's say my range is defined as the sample frequency by 2, because I have centered at 0, sample frequency by 2 negative. So this negative and positive thing is because I have centered at 0, right? So I want to translate this frequency and convert it down and bring it to the center point. Okay, so what I should do is I should downsample this particular part, and I should be able to bring it to the center. Now here I can easily analyze, I can easily create a small filter just to analyze this frequency. Okay, so we also use an anti-aliasing between these steps. So this frequency translating FIR filter contains all of that. So it does this work for us. It brings down the desired frequency to the center so that you can analyze it. Of course, you can change the center frequency by adding some center frequency value here, as you can see in the properties block. So if you are not giving center frequency at 0, you will pass a value, and then this translation will bring a particular frequency to this value, whichever you have mentioned as the center frequency. Okay, so let's just run this thing. Okay, one more thing you need to add here is, so this thing is you can follow into the documentation, this part, the tabs part. So it's a value you have to pass, which is in a proper format. So you have to pass the sample rate, and you have to give sample rate divided by twice the decimation values. And you have to define a transition bandwidth, which I have defined as a 2000 here. So these parameters you have to pass to a function called FIRDES.low_pass. It's basically a low pass filter. So you want to bring your higher frequency to this low pass filter range, and then you want to analyze it because it will extract the other noise, other higher frequencies. So transition bandwidth, of course, is required. And center frequency, as I mentioned, you can pass a center frequency value if you don't want your frequency to be centered at 0. And then, yeah, I should explain this clock recovery module here. It's not of it is a different kind of thing. Basically, we are using it just to recover the clock losses we have been facing while we are moving from this channel model to translation of the frequency. And then, so before passing it to the low pass filter, we need to add this clock recovery. You can go to the documentation to find out what parameters exactly you have to give to this block. Okay, then we have a low pass filter where we are not changing the decimation value and the gain value, and sample rate is defined, cutoff frequency and transition width should be defined. Let's just execute this. Okay. All right, so you can see I just wanted to show you how an amplitude shift keying looks like, because we studied this in the previous part of the presentation, and I wanted to show you how you can just visualize the amplitude shift keying and other kind of modulation onto the GNURadio. So here you can see that amplitude is continuously changing, and it is changing between two levels, a high and a low, and nothing else, right? So there are only two levels of amplitude here. How it will look like when it is amplitude shift keying is done. So it looks like this, because in the upper part we're just having a amplitude shifting signal. So this low frequency signal is supposed to be the information signal, the message signal, which we denoted as the M of T. And we added a high frequency carrier signal, and the amplitude shift keying modulated signal looks like this. So here you can see that continuously changing between two levels of amplitude, but it never goes to zero, because the base signal, the baseband signal was never going to the zero. It is hovering between 1 and 3. So that also comes reflected into the amplitude shift modulation here. So it will never go to the zero. If it goes to the zero, it will be like loss of signal there, because you won't be able to define it as it is no signal or a zero signal, right? So this is how the amplitude shift keying modulated signal, or we generally refer to as on-off keying, is it looks like. So you can create your own modulated signals to visualize the waveforms, so that you can learn about different type of modulations. One example I can give you is most of these remotes we use for let's say if there is a plug point which you can operate through a remote, just pressing a combination of buttons. They use this on-off keying type of thing, or it's, let's say it's a door opener, or it's a remote for turning on and off a light or a bulb or something. So these basic type of remotes we use, they operate with this on-off keying scheme, and they have a combination of switches which defines that what should be how your signal should be converted into a digital 0-1 stream. So if you try to record a signal from such kind of remote, you will probably see the similar kind of waveform there. So you can easily identify that this is on-off keying, this is amplitude shift keying. It's not some other modulation. So if you work on creating different modules for different type of processing, different type of modulation schemes, you can easily rectify that if you in future capture any signal and you are able to identify what kind of modulation it is just by looking at the waveform. So for on-off keying, it's pretty much simple because it just turn on and off. So yeah. All right. Okay, so I think before moving to the software-defined radio part, I will just take a break of let's say 5 minutes, and then after 5 minutes we'll join back. So we will be having 1 hour for the software-defined stuff, and in case you guys are having questions, because I haven't been able to read all the questions and to answer all of them, so I'll answer them. Okay, let's take 5-minute break and then join back. Okay, so those of you who are not aware about this software-defined radios, in simple language, as the name suggests, that it is a radio, but it's not defined in the hardware, it's defined with the software part. So software-defined radio, if you look for the definition on Google, it will show you as it's a radio communication system where the components that were traditionally used in the hardware are all implemented together in the software. So these components may contain all the analog and digital components the hardware was using, like mixers, your filters, amplifiers, power amplifiers, also even the modulators and demodulators. Sometimes they also use the decoders and coders. So software-defined radio means all this type of components which we generally use in the signal processing modules, signal processing equipment and devices. They all have been built in a software application, and you can just directly use it without paying too much for costly equipment. So sometimes the software-defined radio are embedded with the hardware as well, because in order to receive and process a signal, you first need to capture a signal from the outside atmosphere. So for that, you need a specific hardware, which includes the antenna, which includes the radio frequency filters, which includes the radio frequency cables, all sort of that stuff. And then you need a software application which can do all kinds of signal processing for you, which was earlier done conventionally or traditionally by some piece of hardware. So a basic SDR system can consist of a big computer or your laptop, or it can also be a small application running on a Raspberry Pi. So it can be dependent on the type of application you require your software-defined radio to be working on. So it can also be a whole-scale system which has some embedded system hardware and also this software application. So if I just want to give you an example, let's say that I have a Raspberry Pi which is running a software piece of signal processing module. Let's say we created a signal processing module in a Python script and we dumped it on a Raspberry Pi and we connected an antenna to a Raspberry Pi. And now this Raspberry Pi is working as a signal processing hardware, but in the back end, the processing part of the signal is done by a software, because Raspberry Pi does not contain any power amplifiers or radio frequency mixers, radio frequency filters. It doesn't contain that. So in order to reduce the price of such kind of hardware, such kind of embedded systems, we come up with solution which is called software-defined radios, where we just program everything, every technique we use in the digital signal processing. So software radios have very important role in the military and especially the mobile communication, because you can imagine your mobile to be a whole-scale computer, signal processing computer, because it processes a lot of signals, your Wi-Fi, your Bluetooth, your mobile signals, your NFC. These days, the mobile phone comes with the NFC as well. It also does the image processing for you, reading your Face ID, your thumbprints. It does a lot of signal processing, especially digital signal processing. So you can see your mobile phone as a signal processing equipment, not just a piece for communication or for chatting on WhatsApp. It's a very sophisticated and very complex device. It contains a lot of technologies which we don't generally get access to in other part of our daily life. So it's very interesting device. And yeah, of course, in military, it is very much required for those people to build some applications which are only specific to them and which are not known to the other people, because they cannot demand from the outside manufacturer always to build the specific hardwares for their applications. So military is now switching to the software-defined stuff. Actually, it was the military who came up first with the software-defined radios concept. So it has very wide applications ranging from like all sort of levels. Some hobbies, they use the software-defined radio hardwares like HackRF or RTL SDR or USRP, and then they build some Python script or GNURadio module on their computer, and they are able to do all the stuff which for which they need to buy sophisticated equipment. Now they don't need to buy that. Okay. So as you can see in the diagram, whatever I explained, it is basically that. So you have on one side where your baseband is processing, you can have any kind of hardware, whether it is a FPGA. If you don't know what an FPGA is, it's a field programmable gated array. So this is actually where a hardware where you can program your own architecture of even a microcontroller or a microprocessor. So you don't need to buy a specific microcontroller for each application. You can just design your own microcontroller or a processor on a FPGA and just run it. So basically, if you want to create your custom architecture, you can use the FPGA. Then there are ASICs, there are microcontrollers, microprocessors, and in the backend there are always a software which is communicating between your hardware and your processing module, or maybe your input-output ends to the environment. So on the radio side, the end portion is always an antenna, because without an antenna you cannot interact with you cannot make your equipment interact with the environment, with the atmosphere, because all the signals which are flowing in the environment are in analog form. There is nothing digital flowing on here. So in order to capture those signals, you need an antenna, which is analog device. So I think for software-defined radios, this is the only component where you find the proper analog thing. Yeah, of course, there are some hardware, they contain some filter ICs and all those things to filter out initially before you go to the programming part of the software-defined radio. So they do this with some pieces of hardware. Otherwise, you can do all the stuff in the software itself. And there is analog to digital and digital to analog conversion requirement whenever you use such kind of device, whether it is a oscilloscope, it is a spectrum analyzer, or it's a software-defined radio kit generally available in the market for hobbies. So it is always an analog to digital and digital to analog conversion going on between the software part and the hardware part. All right. These are some commonly available software-defined radios, very famous. Most of the people use either one of them or maybe all of them, if they are really a signal or radio frequency enthusiast. So the most common one is the RTL SDR dongle. You can easily find it in the market. It's the cheaper hardware with a lot of functionalities. They have this rtlsdr.com blog website where you can find all the articles and the projects related to RTL SDR dongle published till date, and you can just try building those projects on your own. And there are very, very interesting projects where people have been able to pull out the images from a weather satellite. So this satellite is not even communicating to them, but it's just broadcasting the image to the ground station, and people were able to receive those images with using this simple, cheaper piece of hardware, which we call as RTL SDR dongle. Then we have HEC RF1, which is another very famous and common device, and it has an increased range up to 6 gigahertz and an increased sampling rate. So it is a very, very convenient device to use. It's built for convenience, but the thing is, it has only one RF port where you can connect your antenna to either transmit or receive at one time. So it's not full duplex, it's just a half duplex software-defined radio. Other than that, we have Ateet USRP, which you see this white color box here with 4 ports. So USRP B210 is quite famous. It's a smaller software-defined radio. Okay, I'm not sure what part was missed because it got disconnected because of the Wi-Fi problem. So if you can just remind me, any one of you can just remind me where it got disconnected, I will just continue with that.
USRP.
Okay. So it's not much. Yeah. So USRP is basically if you want to pay a good money for professional stuff, for professional applications, you can spend like 12 or $1,300 for this, because it is a full duplex and it has 4 ports. So basically you can connect 4 antennas and you can transmit and receive. So you can even create your own transmitter, and on the other end you can create a receiver and you can communicate. It's very simple to use. The only problem is if you are using a Linux system and you don't have the software for the USRP. Building a USRP on the Linux system is quite time consuming, but once it's done, it's very easy to use, and it is compatible to almost all the software development applications we use for the SDRs. Also, it gives you facility where you can use LabVIEW and MATLAB projects directly with the USRP. So if you are looking for something very professional, you can switch to USRP. It is costly. The only thing is the cost. And then we have the Lime SDR, this blue color device here. It is Lime SDR. It is being developed by Lime Microsystem. It is a mid-range kind of SDR falling towards the high range. So it is, yeah, it's not very expensive, but not very cheap either. Then we have the Blade RF. So if you go to the Blade RF website, the new and Blade RF website, you will find there are a lot of different models of these Blade RF. So some are having 2 ports, one transmitter and one receiver. Don't just be confused with these extra ports for clock and reference signals. Just we are just talking about the transmitter and receive port. And in the latest models of the Blade RF, they have introduced 4 ports in one kit, and you can also do the multiple input, multiple output analysis on the Blade RF. The signal processing, sampling rate is very high, and the range of frequencies is also very high. So you should check these SDRs. Very helpful. And if you are just beginning with the SDR stuff, I would suggest that you should have at least 2 SDR. So one should obviously be the RTL SDR because it's the cheapest one. There is no point to not buy this. And if you talk about the support online and the community projects, RTL SDR is having the most number of projects because it's like very cheap, and even the people who are not very much enthusiastic about the RF stuff, they can even buy and build some small applications for fun. And another one, you should always buy a full duplex SDR for if you want to build some interesting projects where you also want to transmit and to receive it on another end. Maybe you would like to test your own communication protocol if you have designed any. So this thing you can do, or maybe you want to analyze the communication before implementing it to actually deploying it to some specific application. You want to just run it and test it, whether it is performing as per your requirements. You can do it by just connecting 2 SDRs communicating to each other and not deploying it into actual facility wherever you want to do it. So people use USRP for that stuff. With USRP, you can find a lot of interesting projects, but they are all like big application projects. So I would suggest that you go from a lower range to higher range. Eventually, you will learn about the software-defined radio and more about the radio frequency stuff. And one more thing I should mention here, that whenever you are buying a radio device which has a transmitter as well, you should always check with the rules in the specific country you are living in, because it happens in a lot of cases that you purchase a radio device from somewhere online and it never reaches to you because of the custom issues. So always check with the authorities and the rules, and if you are compliant with that, only then go for purchasing a radio device, because either you will lose money or in worst case you can go to the jail also if you have bought a radio device and you are found transmitting something on a licensed band. So just take care of these things, and I would recommend that only um, buy those SDRs which are allowed in your country. So you can check with the rules in your country. Okay. Here's a list of the SDRs. Let's begin with the actual signal hunting. Okay. So far we have looked into how we can use the GNURadio for the signal processing thing. Now let's just use it with the actual hardware. So right now I have a HEC RF1 connected with my computer. You can see if you are running a VM, you have to connect your SDR going to the devices option, and you have to connect it through the USB. Just select your device with the device ID or the name showing up there, and done. If you are directly running the OS on your computer and not on the virtual machine, then you should be able to directly connect it. Make sure that you have all the drivers for your SDR. So those people who have faced any problems with the RTL SDR, they should just follow the installation instruction on the RTL SDR website. And there are a lot of sources where you can find the RTL SDR installation. So for RTL SDR, the important thing is to install the device drivers. Some on Windows laptop, it doesn't always work. So you have to sometimes install the drivers. Otherwise, if you can just check if it is running in the first place, you don't need to install any additional drivers. So for Linux people, it's pretty easy. They can just check by passing a command ls USB if their device is connected or not. So Linux people can just use the command line. Okay, so I have the HEC RF connected here. So I told you about the command to install the GNURadio, sudo apt install GNURadio. Also, after installing GNURadio, there are some things which if you don't find in your GNURadio installation, you have to include them externally. So if you can search Osmo, it's Osmocom sync and source showing for me here. If you don't find it here, what you can do is you can just try installing sudo apt install gr-osmo SDR and press enter, and you should be able to see this module here. Sometimes it happens that if you are installing a very older version of GNURadio, you might not find the Osmo SDR thing here. So this Osmocom utility is required to connect the HEC RF with the GNURadio. So I have Osmocom source. This will work as the input from my HEC RF device, and I'm passing this input to a frequency sync. So let's just begin. I will say signal 1, a GRC. All right. Okay. So now I'm not tuned into any particular frequency. I'm just I have just given 100 mega frequency here. You can see, you will always see when you are using a software-defined radio, at the center frequency in the FFT domain, you will always see this peak. So this peak, don't be confused that this peak is a signal. No, it's not a signal. It's just where your center of the band lies. So you are right now you are focusing on the center frequency 0. It's 0 kilohertz showing on here. Okay, let's now try changing. Sample rate. We have the frequency 100 megahertz. Okay. Okay, so whenever you open a Osmocom source or an RTL SDR source, there are a bunch of things you need to take care of. Sample rate, it's the same thing that we have discussed earlier, and you have to mention a frequency you want to tune in. So you will give a channel 0 frequency where you want to tune in, and then RF gain is another important thing. So sometimes it happens that the signal power is very low and your radio frequency gain of your antenna is not it is not sufficient. So sometimes you might lose capturing any signal just because of the gain of the antenna. So in order to be on a safer side, use antenna gain to be between 20 to 30 dB, or you can just check if you are able to receive the signal with just 10 dB gain, because 10 dB in some cases it's more than sufficient. So, and you don't want to increase your gain to a very high value because it can damage your device. Not with this software stuff. The most it will do here with the software radio is that will stop working. But in other cases, when you are actually using a hardware, if you increase the gain to a very high level, it might damage your antenna as well, or your input port of the device, because it will be capturing a lot of power. It will be giving to the device, which maybe your device is not made for. So just take care of that. Some of you might not be having the hack RF, so you can just use the RTL SDR, and you can use the RTL SDR source block here and the FFT sync or QT frequency sync. Okay, so now in order to process a signal, I need a bunch of things in my signal processing module, because right now I'm looking for actual signals, right? And for the actual signals, I want to see a lot of things. I want to see the waveform. I want to see the frequency spectrum. I want to see sometimes the time domain waveform as well for some particular type of modulation schemes. So now let's just build a very simple spectrum analyzer on GNURadio. But before that, I must show you something which might be helpful for your convenience. There is a software called GNURX SDR. So if you are running a Linux system, just type the command sudo apt install GNURX SDR and press enter. And GNURX is a very simple spectrum analyzer, and it's very small application. It's not very heavy, but it does a lot of work. It solve a lot of problem for you in the signal processing domain. So if you are just starting with the SDRs and signals, you should use GNURX first to start with your simple exercises. So I will just run the GNURX module here. So right now I'm connected to the hack RF. So okay, it's showing a pipe error because my hack RF is already connected to GNURadio. All right. Okay, so when you run the GNURX, it will pop up this screen where you need to configure some settings. So if you click yes, you will be configuring the IO devices. So here it might give you the option to select your device particularly, or it sometimes just identifies your device and just take it as an input. You can also select the sampling rate values here. So right now I have a sampling rate of 8 megasamples. You can define a bandwidth. Right now, I'm not defining a bandwidth. It should take by default. And just press OK. All right, it has failed again. Let me just disconnect and connect it again. This problem often happens when you are working with a virtual machine and connecting your USB device with the virtual machine. Especially with HackRF, this piping problem is very common. Let's just try it once more and see what's happening. Let's say I take a sampling rate of 10 megasamples. Okay, it's not working for this. All right. Okay. Yeah, it's up and running. So this is some problem which you might face with the GQRX and HackRF very often. Don't be just disappointed with that. Just try looking for the solution and you will find one. So this is how this GQRX utility looks like actually. And you can just start connecting your device and just start looking into the signal directly without doing anything. You just have to play this button here and it should show up the signal coming in here. Okay, so I think my device is not yet piped very well. It has opened the utility but not the connection with HackRF. I should just close it. It's connected. Okay, I think I should just remove the HackRF and I'll show you the thing with the RTL SDR. Just give me a moment. Just connecting the RTL SDR right now. Yeah, so it shows up here. All right. Let's just run GQRX. I want to connect to the RTL SDR. Okay. I'll just check if it is running with the RTL SDR or not. Okay, here also it's not running. I think there is some issue with the port. Yeah. So this is for the RTL SDR, which I'm running right now. So in this utility, you'll find a bunch of options which are very convenient for your signal analysis. So on the right side, you'll find all the options where you can change the filter weight. You can also have some demodulations here. So if you don't want to demodulate the signal, you should just select demod off. It will just give you the raw signal the antenna is capturing. Then if you want to analyze the raw signal, but in the IQ format, you can select the raw IQ. If you think that your signal which you are analyzing is the AM modulated signal, so you can select the AM. Similarly, the other options are here. So let's say if I select the WFM, so it gives me the wideband frequency modulation. There are two options, stereo and mono, and I think you all know what stereo and a mono. So now let's just tune to some frequency. Right now it's tuned to 871 megahertz. So you can just, okay, let me just increase the lower values first. All right, so I want to tune into some FM radio frequency, which I am not able to see here because of the geographical location where I am right now. I'm right now in a very remote region. Let me just increase the gain values and also the, where is the reference level? Okay, it's already there. All right. So currently, right now, I'm at a geographical location where it is really difficult to find FM frequency. It's really remote into the desert. So I don't think that I should be able to find a FM band here. Let's just look for the GSM band or other frequencies. Yeah, these small peaks you are looking here are some sort of carriers. They look like that. So if you observe such frequencies, see, if I reduce the gain, I'm not getting anything there. If I increase the gain, there is something here, right? I'll just move into some frequency where I can show you some data. So simple thing is that you can move your cursor here. You can use the mouse to tune into the frequencies you want to analyze. And here in the yellow and blue region, you can identify which frequency has how much amount of power. So the signal which is having more power will show up highlighted in this screen. So this thing we call waterfall display. So it is very important to analyze signal in all the domains. Specifically, the spectrum analysis is required and the frequency domain analysis is required in order to extract out the simple information like what can be the power of the signal, the strength of the signal, and what can be the correct frequency, exact frequency of the signal. Let me just tune into one more band, and then yeah, here I can see something, right? Okay, so now you can see there are some movements on this waveform, and these movements are associated with some signal flow. Also, if I may show you, okay, I have reduced the low noise gain here. Yeah, so these, you see these deviations and these color changes in the waterfall image. These are all associated with some signal flow, right? So this band we are right now tuned in is the starting of the GSM band, which is associated with the mobile communication. So whenever you see this highlighted yellow thing happening here, that means there is some sort of communication happening in this band. And let's tune further. Maybe we can find some specific packets here. All right, let's move to the 900 band. So this GSM frequencies, there is a defined band for GSM frequencies, which starts from 800 megahertz and ending up to 1800 megahertz. But you have to check that what are the active frequencies in your location, wherever you are, in which country you are. So you have to check for the bands that you have there. All right, so I saw some observation here. If you can see in the middle, okay, if you can see in the middle, there is some movement, and I can see the peaks here. I'm not sure if you guys are able to see through my screen, but if you have the GQRX downloaded, maybe you can. Now I have increased the gain, and now I can see that there are clear disturbances on this baseline. So I can say that this is something, this is some signal related to some communication happening here. So this is the GSM frequency 951. Then we can tune into furthermore. Okay, so you can see the clear difference on when we are tuned to 952, which is basically the center frequency. We cannot see much happening here because either the amplitude of the power of this signal we are capturing with our antenna is very low, or it may be just like nothing but a side band or very low amplitude level of residue signal there. But if you look at the other part, which is coming up as highlighted orange portion here on this waterfall image, this signal is showing us disturbances, which is clearly means that some kind of communication is happening here. So that's how you can detect a frequency where some intended signal communication is happening, or maybe it's a point of interest for you if you want to analyze that particular signal there. Also, you can see at 952.2, there are bursts of signal going on around here. So all these orange lines, thin lines you can see in this screen, they are all bursts of the packets. So they are packets data going on like at random periods. So this is related to the GSM telecommunication part, that where the mobile and the cell tower, they communicate with each other, some broadcasting some IDs to each other and some numbers, IMSI numbers or TIMSI numbers. So this is happening a lot here in this band. That's how you can tune into several frequencies and look for your intended signal. So sometimes when you are tuned into exactly right frequency, you should be able to see a lot of stuff happening there. Specifically, to start with, if you know a known FM radio station in your location, you should just tune into that. Sorry. And you should be able to listen to the radio station without doing any great efforts. You have to just select the demodulation as to WFM stereo, and you should be able to listen to the radio station. Unfortunately, there is no radio station I can hear because of the geographical location I'm at. All right. So this is a spectrum analyzer which gives you, so the range of this spectrum analyzer will depend on the range of your device. So you should check with your device what is the lowest and the highest frequency range and what are the sampling rates your device can support. If this device is supported by the GQRX tool, you should be able to find all these options already there in the GQRX configuration settings, and then you have to just select it. Okay, so now this is already built module here, GQRX software, but you can do the same stuff with the GNURadio as well. Okay, here you can see on the screen that I have built a similar type of tool with the GNURadio. It took me just few minutes or maybe just less than a minute to build this module. The simplest thing I'm doing here is I'm using a Osmocom source for my HEC-RF, using a throttle to maintain the sample rate, and using these two sync blocks to look into the frequency and waterfall image display. And I'm also using 3 range values. One is for the RF gain, where I'm defining my RF gain for the device, for the antenna, by a slider. I'm also using a range value, a slider value for tuning into the frequency and also for the bandwidth. So this simple GNURadio module you can build, and this will work in the same way as your GQRX for looking into the signal. So let's say you don't have any GQRX with you. All right. So this looks similar to the GQRX, but this is not something which you have downloaded. It's something which you can make on your own. All right. So simple thing you can do is you can change into the RF gain and the frequency values. Let's say I move to some frequency which was in the GSM band, where we were looking at the options. Okay. I could have shown you a lot of signal stuff on the GSM band, but right now I'm at a geographical location where there are very few things like that. That's communication thing going on here. I cannot even receive a frequency modulated signal here, any FM radio station. So that's how you can build a small, simple spectrum analyzer for your application. And this is just one simple example for the SDR with working with the GNURadio. You can also add a lot of things into this GUI by just using the blocks here, and you can also change the properties inside the blocks. Let's say if you want to clearly see whether you are getting a signal or not, you would like to do the averaging of the signal. Okay, that option actually shows in the WXGUI. All right. And in the similar way, you can build another type of demodulation modules which can directly work with your RTL SDR or your HEC RF or your Blade RF, even the USRP. For USRP, you need to add USRP source. So you type UHD, you will find USRP source or sync, and you can just drag and drop and do the settings there. So this is a FM receiver which I have built here, and it's very simple thing. I have just used the Osmocom source as the input, and I have used the throttle to maintain the sample rate. Then I have used a DC blocker because I don't want any constant signal coming in and interfering with the signal I want to tune into. And then the low pass filtering I have done to to reject the higher frequencies, because any FM channel is having a bandwidth of only 20 kilohertz, 200 kilohertz, and you can find the other side-by stations, the closest stations also interfering into the station you want to tune in. And then we have to maintain the sample rate. So here, one important thing you might note here is this low pass filter, I have changed the decimation value to some factor here. So I have changed the decimation value to a factor of 5 because I want to reduce the sample for this particular processing block. And then I have to make up for this loss in the samples in the further stages. So I have used a rational resampler. So basically, rational resampler gives you an advantage where you can define the interpolation and the decimation data together. So I have given the interpolation as to 12 and decimation as 5. And then further, I have used the WBFM receive, which was basically you saw in the GQRX as a WFM stereo. So I have used the WBFM receive from the GNURadio. So it will directly demodulate the FM signal and it will convert it down to the audio signal I want to listen to. So this audio signal, to listen to the audio signal, I need to have an audio sync. And for the audio sync, I have used 48 kilo sample rate. Now, let's just execute. Okay, so I can tune into the different channel frequencies here. Unfortunately, I'm not getting any FM radio signal here at this location. You can also adjust the gain, audio gain. I have used just 2 sliders. Okay. So you can even build a small FM radio receiver just using an RTL SDR or a HEC RF1. You don't need to buy a FM receiver just like we used to listen to in older times. We used to have this FM radio transistor. You can do the similar stuff. There are a lot of open source projects with the RTL SDR, HEC RF, Blade RF, and USRP as well. And it is up to you how much deep down you want to go into. So I remember that one of the participants had asked about how to exactly identify the sampling rate for our processing module. So I would suggest that there is no hard and fast rule for the sampling rate, but just one. You need to sample your signal with at least twice the sample rate. So if your signal frequency, let's say, is 100 kilohertz, you need to sample it at least for twice of the frequency, so that you have sufficient amount of samples to process this signal, and you need to recover the information in the output side. Now, if you are going to increase the samples, that's basically the oversampling. If you are sampling at a very high rate than the Nyquist rate, you need to add some decimation and interpolation modules to maintain the signal, to maintain the sampling rate for your processing module. Also, you need to take care about what is the output module of your flow graph. So let's say I want to use an audio sync here, and the audio sync can have only the 48 kilohertz sample rate. So I need to maintain this sample rate before my signal enters into this audio sync. So the block which is here at the input side of the audio sync, I need to maintain the sample rate of 48 kilohertz. That is why I have added a quadrature rate of 480 kilo and did a audio decimation of 10. So if you divide 480 kilo by 10, you will get 48 kilohertz. That's how I'm maintaining the sampling rate throughout my flow graph. And you need to, if any error comes up or it doesn't work as per your requirement, you need to actually look into the sampling rate first, and especially if you are working with the GNURadio. So also, sampling rate depends on what kind of signal you are looking at. So if you are looking at the audio frequency signal, the maximum audio frequency signal which is audible to the human ears is 20 kilohertz. So apparently you should use 40 kilohertz as a safe side sample rate. That's why we have 41 or 48 kilohertz sample rate in all type of audio signals we listen to, whether it is an audio card in your laptop or it is a CD which is containing some audio or a music. So in order to convert it to the audio, you need to have it have a sample rate of double, at least double. And whatever your frequency is, you need to have a sampling rate of at least double to actually extract out sufficient amount of samples. So I think that concludes this workshop, because even we conducted this workshop for 4 hours, and it is still very less to go into all the details and everything. So I have just explained to you the important concepts you require for the GNURadio and for the software-defined radio to start working on looking for the signals. There are a bunch of interesting projects which you can always refer from the internet. I didn't want to just consume the time building the same projects which you can just find on GitHub or some other website. So I decided to cover up all the important topics and techniques of digital signal processing and GNURadio. I hope that you will like to build some more projects on GNURadio, and if you have not yet bought any SDR, I'm sure that after this workshop you are going to buy one and start doing the signal hunting for things. So here I will just conclude this workshop, and I'm hopeful that you will find a recording of this workshop after a while. In case you have any doubts or you have any specific questions, you can just email me on this email ID, and I'm always reading the emails, so I would probably reply back to you with the answer. And if you guys want to have a good list of projects, you can also ask me. I can provide you that. So I thank you all for attending this workshop. Also, I would like to thank the organizers of HITB. I would like to thank my team in Zenith Labs who supported me throughout this presentation. And once again, thank you all for attending this workshop. And yep, so we conclude here. Thank you very much. And I'm hopeful to receive interesting questions from you guys on my email. I will just write my email on the chat so that you don't miss. This is the email. Okay, I just want to spend a minute to see if any questions are unanswered, and then I'll just finish this workshop. Okay, so those of you who don't know this person in the chat, Harshit, who is answering all your questions and supporting me throughout this workshop. He is actually a part of my team, but not yet joined my team, but working remotely. So a special thanks to Harshit for answering all the questions which I couldn't even read. Thank you very much. I appreciate it, man. And I'm hopeful that you guys will send interesting questions. I'm available on the email. If you have not yet got the email ID, then please note it down from the chat. All right. Thank you very much. Thank you, HITB, for giving me this opportunity to present this interesting workshop here. It was quite a long workshop, but still we weren't able to cover almost everything we wanted to, but yet it was a good and interesting workshop. Thank you, everyone. Have a nice day. Good luck.